So as we discussed, the homography is the transformation matrix that takes you from one plane to another plane, but through a point of projection. So let's first take a look at why this is relevant to the problem of image stitching, and then we'll talk about how to compute the homography. So let's look at the following problem. You have your three-dimensional world right here, and imagine that you take one image of this world, this scene, using this orientation of the camera. So this is your image right here, and this is your image plane 1. And then you rotate your camera, and you take another image, and that falls on plane 2. And then you take a third image that falls on plane 3. Now, let's define another plane right here, which is plane P. And we know that there is a homography that relates plane 1 to plane P, as they share the same center of projection. So you can map your image on plane 1 to plane P using a homography which is H1P. I'm going the other way again, from 1 to P. And you can take your second image now, which lies on plane 2, and you can map it to the same plane, and you can see it as mapping plane 2 to plane 1, which is using 2 to 1, H21, and then you're multiplying that with H1P. And you can do the same thing to the third image as well, which lies on plane 3. So this tells you that by using, if you share the same center of projection, and you take these multiple images, you can actually map all the images to a single plane by simply computing the homographies between the images. So this is very useful to us in stitching panoramas. Okay, so how do we go about computing homographies? Let's start with the problem of just two images. You're given these two images here, image 1 and image 2. You apply your SIFT feature detector, and we're going to match them, and we get all of these matches. Let's say we get these perfect matches right here. So given a set of matching features or points between images 1 and 2, we want to find the homography that best agrees with the matches, that best takes you from image 1 to image 2. Once you computed this homography, once again, you can essentially warp image 1 to the coordinate frame of image 2, or vice versa. So when is this valid? When is this homography actually useful in this kind of a situation? This is a very interesting point that we should give some attention to. Firstly, it's always valid if you're capturing images of any three-dimensional scene, however complex it is, but from the same viewpoint. No problem there. We know that all the images are related via homographies. Or it's still valid if you're actually imaging a plane in the three-dimensional world, and you're taking these images from any viewpoint. So let's say you take one image of a plane from here, another image of a plane from here. Well, no problem, because this image that you've captured in this camera is related to the plane in 3D by a homography, and this one is also related to the plane by a homography, and therefore there exists by composition a homography that takes you from this image to this image, even though they're not being captured from the same viewpoint. And then the last case is, yes, you're not exactly in the same viewpoint, and this is what typically happens when you capture a panorama. You hold up your camera and you take a picture here, you take another picture here, another picture here. You're not necessarily spinning the camera around exactly its center of projection, but it typically is equivalent to a single viewpoint or center of projection, simply because the scene is far away from you. So if you can assume the scene is really far away, then you're really assuming that the scene itself is a plane at infinity, and therefore, again, the homographies hold, even though your viewpoint is changing somewhat. So now let's talk about computing the homography. So here is a point in we'll call this the source image, and this is your destination image. So after we compute the homography, we might imagine that the source image gets warped to the destination image, or its coordinate frame. So here you have a point in your source image, xs, ys1, Here is the homography that you are trying to compute, and you have xt, yd1 in the destination image. So one question to ask is, how many unknowns do we have here? Well, there are 9 unknowns here, of course, but for reasons that we mentioned earlier, the fact that we can only compute the homography up to a scale factor, we really have 8 degrees of freedom here. And so how many points do we need to solve this? Meaning to say, how many pairs of matching features do we need? Well, it turns out that the minimum number of matching points that we need is 4. But, of course, you never want to do it using just 4. You want to use all the matching pairs that you can, because that's going to make your estimate of the homography more robust. So let's see how we can compute the homography now. Take a look at this equation right here. We're going to basically write it out. That is, we are going to multiply this vector with this matrix and write down the equations for xt and yd, and you get these 2 equations. I should mention that we have introduced the superscript I here, and that corresponds to the index of the matching pair. So that I goes from 0 to n, where n is the total number of pairs that we have at our disposal. So that's the same equation here. And now what we're going to do is take this denominator right here and take it to the left-hand side in each one of these 2 equations. So you get this. Now again, remember that all the x's and y's are known to us. It's the h's that we're interested in. Now we can take these 2 equations and write it in matrix notation right here. So here, this matrix that you see here has 2 rows, and that's because you have 2 equations here. But it includes all the x's and y's, which are the knowns. And then you have this vector right here, which has all the unknowns, which are the elements of H. You have 9 unknowns here, equal to 0. So of course, we can't solve this with 1 pair of matching points. We know that we need a minimum of 4 pairs, but we probably have many more than that. So what you do is you essentially stack up all the rows of corresponding to the different pairs of matching points, and you get a large matrix here. This is an overdetermined system of equations. You have a large matrix here of all knowns. We'll call that A, multiplied with your unknown vector H is equal to 0. And so AH is equal to 0 is the equation you want to solve. But of course, you can get a trivial solution here of H equal to 0. We don't want that. So we add a constraint here, which is that H squared, the magnitude of H, is equal to 1. So I should mention that problems of this form, AH equal to 0 such that H squared is equal to 1, they pop up very often in many different domains, not just in computer vision. So it's a very common problem, and we solve it using what's called constrained least squares. So we want to solve for H such that AH is equal to 0, while H squared is equal to 1. And so we want to define this as a least squares problem, where we want to find H that minimizes AH squared such that, that's why it's least squares, such that H squared is equal to 1. And we can now rewrite these 2 terms as follows. AH squared is equal to AH transpose times AH is equal to H transpose A transpose AH. And H squared can be written as H transpose H, which is equal to 1 right here. So that's what we want to do. We want to find the H that minimizes this such that this is true. So for this, we can define a loss function L. So this is the loss function. These are those 2 terms here, and we're putting them together by saying this minus lambda this is your loss function, and we want to find the H that minimizes L. How do we do that? We find the derivative of L with respect to H and set it equal to 0. And when we do that, we get this very simple expression, which turns out to be the classical eigenvalue problem. A transpose A H equal to lambda H. So what we want to do is take A transpose A and find its eigenvalues and eigenvectors. And H that we are looking for is the eigenvector that corresponds to the smallest eigenvalue of the matrix A transpose A. And there are many functions available, code out there that you can use to solve this problem. For instance, in MATLAB, you use this function right here. It returns all the eigenvalues and eigenvectors of a matrix, in this case A transpose A, and you take the eigenvector corresponding to the smallest eigenvalue, and that is the H you're looking for. That's a vector. You're going to now take the elements of this vector and rearrange them into a 3x3 matrix, and you have your homography. So let's recap what we have done here. You have two images. You've applied the SIFT detector to these two images. You found matching pairs of points. You're going to take all of these matching pairs, which is represented as XD, YD in one image and XS, YS in the other image. You're going to take all of those coordinates and construct a matrix A, as we showed earlier. Then you're going to take A transpose A, and you're going to find the eigenvalues and eigenvectors of that matrix. And the eigenvector that gives you the smallest eigenvalue is the H that we are looking for. You rearrange the elements of the vector H and you get your homography matrix. You're done.